Hello, welcome to the first video in the Labtainer walkthrough series. Labtainers are virtual machine labs provided by the Naval Postgraduate School, built to give students hand-on experience with cybersecurity concepts. These labs and their manuals can be found at mps.edu. In this video, we explore the Labtainer bufoverflow, which explores the software vulnerability of buffer overflow exploits. We will be tasked with completing the exploit code, performing the exploit, and investigating the security measures used to counter buffer overflow exploits. The security measures investigated include address randomization, stack guard, and non-executable stack. Like any Labtainer, we initialize the lab by running Labtainer and then the Labtainer's name, which for this lab is bufoverflow. Once all necessary resources are downloaded, we can simply hit enter to start the lab. With the lab started, you will see a new terminal called Ubuntu at bufoverflow. This is the terminal in which you will perform the lab. We begin by following the provided instructions to set up the lab. We first turn off virtual address randomization. We then compile call shellcode.c with an executable stack flag. And then we also compile stack.c with an executable stack flag as well as a no stack protector flag. Once everything is compiled, we can go open up the provided exploit.c file using vim and take a look at what code needs completing. As you can see, there is a commented line stating add your changes to the buffer here. Note that the buffer we are working with is 1000 bytes in size and is pre-filled with no op commands by the provided code. We'll need to do two things to complete the exploit. First, we'll need to add the exploit shellcode to the buffer, and then we'll need to overwrite the return address in the stack to complete the exploit. Adding the shellcode into the buffer is simple. Our goal is to add the shellcode at the end of the buffer so that the no-op commands can act as a sled, so that any jump to the no-op sled will slide straight to the beginning of our shellcode. We calculate the offset from the beginning of the buffer where the shellcode should begin, making sure sufficient space is given to the shellcode, and then we replace the end of the buffer with the shellcode using a simple for loop. Now we need to overwrite the return address. This is a bit more difficult, and we need to identify two locations: the location in the buffer that the return address should be placed, and the memory address we would like to return to. We can tackle locating the position in the buffer that the return address is located first. We use GDB to disassemble the vulnerable program and identify the command used to store the buffer. Note the command lea-0x162 ebp eax. This is loading the address location of the beginning of the buffer into eax, which will be used in the function call to string copy. Recognizing that the memory location of the start of the buffer is calculated based off of a -0x162 offset from register ebp, we can now have an idea of what the stack looks like. Since the return address is 4 bytes in size, the beginning of the return address would be an offset of 0x162 plus 0x4, or 358 bytes from the beginning of the buffer. We can now go back to our exploit code and set up the return address overwrite. To figure out the return address, we can use GDB to set a breakpoint within the insecure function bof to identify the memory address stored in the stack base pointer, EBP. Using the resulting value of 0xFFFFD2D8, we can calculate the entry point of our shellcode by using the diagram. With an expected entry point of around 0xFFFFD541, we can pick an arbitrary memory address smaller than the entry point so as to attempt to land in the no-op sled and slide into the shellcode. We can pick 0xFFFFD330 as our arbitrary target. Recognizing that the system memory is little endian, we store the least significant byte of our target address at the smaller address and the most significant byte at the larger address. Compiling and running the command to execute the exploit, we successfully acquire a root shell and obtain the contents of the secret file. We can turn address randomization back on using the following command. With address randomized, our target address is no longer guaranteed to land in our no-op sled and slide into the shellcode because the position and stack we land in has been randomized. In theory, we can smash the stack by repeatedly running our exploit and filling up the entire stack with no-op sleds and shellcodes until we get lucky and our target address ends up as part of a no-op sled. This would work because computers do not clear the values on stack. They only move the stack frame in order to be efficient, so any overwriting by our no-ops and shellcodes will stay on the stack after every run. Because the stack is quite a large space, this process can take a very long time if we are unlucky. Here you can see the results from running the wild bash script. Unfortunately, I was never able to reach the root shell in my attempted runs, but you can see all the segment faults that you get along the way. StackGuard protects against buffer overflow by inserting a small value before the return address so that any buffer overflow attempt will overwrite this value before overwriting their return address. If the program detects a change in the value, the program will abort, thus preventing a stack smashing attempt. Here's what happens when we attempt to run our exploit in the presence of GCC's StackGuard. Non-executable stack means exactly what it says. Items on the stack cannot be interpreted as executable code. Since our shell code is stored in the stack, overwriting the return address to jump to a position in the stack will cause a seg fault. The position jumped to is not recognized as a valid code section by the computer. Here's what happens when we attempt to run our exploit when the stack is non-executable. And that's all for the Buff Overflow lab. Make sure you exit the lab terminal and run stop lab in the original terminal to save your work. See you in the next lab.